Now we are going to start with another compound of boron, and that is the boron hydrides. So what are boron hydrides actually? Boron hydride is a compound which contain boron and hydrogen. That means boron and hydrogens are linked together, and whenever they are linked together it is called as boron hydride. And you know that we have a special name for boron hydride. They are called as boranes. They are called as boranes. And we see that we get to see various kind of boron hydrides, various kind of you can say boranes, and generally they are of two types with general formula BnHn plus 4 and BnHn plus 6. That means variety of boron hydrides we get to see in nature, and but the common hydrides follow this kind of general formula, that is BnHn plus 4 or BnHn plus 6. For example, BnHn plus 4, let's say we have an example B2H6, right? Likewise you can have another member also, and BnHn plus 6, let's say we have an example, that is B4H10. Right. The common name for B2H6 is diborane, right, and for this is a tetraborane. So don't get confused that you get only diborane or tetraborane. It's not like that. You get variety of you can say members belonging to this family. That means having a general formula corresponding to BnHn plus 4 and BnHn plus 6. But you know that the common hydride of the boron is the diborane, which is B2H6. This is the common hydride, you can say. This is the common hydride. And we are going to start we'll be studying the boron hydride in detail. So we'll be considering its common hydride, that is the diborane. That means we'll be taking up reaction based on the diborane only, right? So let us start with a detailed study of diborane, that how it behaves under different conditions. First is that how can we actually what methods actually we can employ in order to prepare diborane. So we have a different preparation in the you can say as a lab preparation, how we can prepare it. In lab we can prepare it by using sodium borohydride reacting with the iodine in presence of a chemical called as diglime. They both react in presence of diglime, and what do we get as a result? We get sodium iodide, we get hydrogen, and along with that the desired product, that is the B2H6, that is our diborane. So this preparation is actually employed in the case of you can say in lab whenever we need to prepare the diborane. Otherwise, as far as industrial preparation is concerned, how we can prepare it? We can prepare it by using sodium hydride and reacting with a compound of boron, particularly BF3. So what we are going to get here, our desired product B2H6 we are going to get, and along with that we are going to get NaF. So this is how B2H6, that is diborane, can be prepared in lab as well as in the industries. So you need to be familiar with both the preparations, because we should know that how we can prepare in lab and how we can prepare in industries. So these are the two methods, that is in lab by reacting iodine with sodium borohydride in presence of diglime, and in industries by reacting sodium hydride with the boron trifluoride, and what we get the diborane. So this is how we can prepare the diborane. Now the question must be striking in your mind that how diborane looks like. So we have seen that it is a poisonous gas. It is a poisonous gas. And as far as its stability is concerned, what we have seen that this diborane is actually stable but only at low temperature. It is stable only at low temperature. But whenever higher temperature is implied, then what happens? At higher temperature it forms higher boranes. That means it forms the you can say if we take the temperature approximately ranging from 373 to 562 Kelvin. right? Then we are going to get the higher boranes of different formulas, having a general formula corresponding to BHN plus 4 as well as BNHN plus 6. So we can get higher boranes depending upon the temperature. But if we carefully adjust the temperature, let's say approximately ranging from 373 to let's say 393 Kelvin, then what we get, this diborane get converted into tetraborane. So definitely like it is stable at low temperature, but at higher temperature it forms different types of boranes, as you have seen that the temperature ranging somehow from 373 to 562 we get higher member of boranes. So otherwise it is stable, but it is stable at low temperature. So this actually can be the method employed in order to prepare different boranes from the higher member of boranes from the diborane. Next is the combustibility. You know that whenever diborane comes in contact with air, it spontaneously burns and catches fire. Now what is the reaction actually involved here? So what happened, like this is our diborane, let's say, when it comes in contact with oxygen, it spontaneously burns and catches fire due to formation of B2O3 and plus hydrogen. So due to this vigorous reaction, or you can say due to a large amount of heat which is liberated, it catches fire, and please do remember that it burns spontaneously in air. And it is not only diborane, otherwise if we talk about the higher boranes also, they also spontaneously burn in air, giving rise to their oxide along with this hydrogen gas. And next we have is the hydrolysis, that what happened when we try to break it in by adding water. So we have B2H6, we add water into it. So what we get? We get boric acid, that is the Lewis acid, a weak acid and a non-protic acid, and along with that we get hydrogen. So this is what we get when we hydrolyze diborane. Next is the reaction with Lewis base. See, this diborane is a Lewis acid. It is an electron deficient compound. So whenever you react with Lewis base, then obviously they are going to link with each other, forming a coordinate bond. So that means B2H6 link with the another you can say Lewis base by a coordinate bond. And I think you remember that what is a coordinate bond? Coordinate bond is a type of bond where the shared pair comes from one group, and like this will be having a lone pair, and it will give lone pair to the B2H6, which is an electron deficient compound. And whenever the bond is formed when the one group is donating an electron but other is not contributing anything in the shared pair, then it is called as a coordinate bond. We discussed in the chemical bonding also. So this is a Lewis acid, so whenever it will react with Lewis base, it will link with a coordinate bond. Now this is an important reaction we are going to start with, that is the reaction with ammonia. So what happened? We have diborane as B2H6. Whenever it reacts with ammonia, it gives rise to an, you can say, a important compound, inorganic compound, which is B3N3H6. And you know that what is it is commonly known as? It is popularly known as Borazine. It is popularly known as Borazine. And if you will see the structure of this Borazine, it will be quite similar to the benzene. What is the structure like? It is particularly, I will draw here, it is just like we come across the carbon and hydrogen in benzene. It is similar like that, that is the hexagonal ring in which you can see the three alternate double bonds with single bond, and H is joined to every atom. So you can see that the structure here resembles the benzene. Otherwise, if you talk about benzene, this is only you can say replaced by C in case of benzene. So as the structure is similar to the benzene, therefore Borazine is actually called as inorganic benzene because they are having the same structure. So this is the reaction with ammonia, where it gives rise to an inorganic compound popularly known as the inorganic benzene, and otherwise it is the specific name is the Borazine with formula B3N3H6. And this is the structure. You should be well known with the structure because you may be asked in the paper to draw the structure also. So this is the reaction with the ammonia. Next, the diborane also form the complex hydrides. How? Suppose we have sodium hydride and we react with diborane. Then they form the complex, that is Na positive, BH4 negative, commonly called as sodium borohydride. Sodium borohydride. So that means it has a tendency to form the complex also. Next, reaction with halogen acid. Suppose you have diborane B2H6. So whenever you are going to add any halogen acid, let's say HX, the general formula, then this X is going to replace one H. As a result, it will be B2H5X, right, and plus H2. And what will be the name for this compound? It is going to be halo, because halo means, halo here stands for any halogen. That can be iodine, that can be chlorine, bromine, fluorine, any. So this is halo diborane. It is going to be halo diborane. So these are all reactions of the diborane. I think you got it. And you know that what is the specific use of the diborane? It is used as a reducing agent. It is used as a fuel in supersonic rockets and also in the preparation of different kind of borohydrides, like we have LiBH4, we have NaBH4. So different hydrides can be actually prepared by using a diborane. So this is all about the boron hydride. I think you got it. That basically is a structure. It is a, you can say, compound with boron and hydrogen, commonly called as boranes. You know the general formula also. And the common this thing boron hydride is B2H6. And we have seen that how we can prepare in lab, industries, and at what temperature it exists as diborane and what happen at higher temperature. And moreover, you are familiar with the inorganic benzene also, that is Borazine. That this is often asked in the paper. And as far as the uses are concerned, we have already discussed. So this is all about the boron hydride, and with this we finished the all the boron compounds, that is the boric acid, that is the borax, as well as the boron hydrides. So these three compounds are, you can say, important compounds of boron that you need to be familiar with. So this is all about the boron compounds and the 30